So, welcome friends to this session of our discussion, which we will continue on the analytical solution of matrix difference Riccati equation. In the previous class, we have started our discussion on this, in which we are defining x k lambda k equal to a matrix H, which is given as A inverse E, Q A inverse A transpose plus Q A inverse E, and this matrix we are getting from our Hamiltonian system, which was defined for x k plus 1 and lambda k. So, in the previous class we have seen that we can find and give name H to this matrix. Then we have shown that with the transformation J as a null matrix of n by n, identity matrix of n by n, we can define J as a 2n by 2n matrix, where J inverse is minus J, and we got H inverse at J, H inverse J. Using the H inverse relation, we have shown that if mu is an eigenvalue of the matrix H, then 1 upon mu is also an eigenvalue of the matrix H. So, this means mu and 1 upon mu are the eigenvalues of matrix H. So, if we are considering a discrete time system, and in discrete time system, if we will see, the eigenvalues lie inside the unit circle and outside the unit circle. If we say let mu is the eigenvalue laying outside the unit circle, inside the unit circle, then 1 upon mu eigenvalues will lie outside the unit circle. So, by this we can arrange these eigenvalues in terms of the diagonal by the similarity transformation. So, this means if M is a diagonal matrix with diagonal element as the eigenvalues of the Hamiltonian matrix H, which are inside the unit circle. So, if M will contain the eigenvalues which are inside the unit circle, then M inverse will contain the eigenvalues which are outside the unit circle. So, we can consider a model matrix W, which is defined as W11, W12, W21, W22, which transform matrix H into the diagonal form, where elements of the W11, W11, W21, this is nothing but one set of the eigenvectors corresponding to the eigenvalue mu. W12, W22 is the another set of the eigenvector corresponding to eigenvalues 1 upon mu. So, W inverse HW is the transformation which which transform the matrix H into the diagonal form, and in this diagonal form my eigenvalues are arranged in the diagonal as the eigenvalue inside the unit circle and eigenvalues as outside the unit circle. So, now my transformation is, let us say using the similarity transformation, we transform x k lambda k as z k del k, multiplying with the model matrix W. So, this means W11, W12, W21, W22 as z k and del k. So, if I will write the transformed Hamiltonian system in terms of the z k and del k, so that will be this W inverse x t lambda t as we have, it should be x k lambda k. This is by mistake because we are using the discrete time system. So, this will be x k and lambda k. So, this will be W inverse x k lambda k here, and this x k lambda k we can write as h of x k plus 1 lambda of k plus 1, and this x k plus 1 lambda k plus 1 we can represent as z k plus 1 del k plus 1 as W of z k plus 1 del k plus 1, and this W inverse HW is nothing but my diagonal transformation. So, I am getting d z k plus 1 del k plus 1, and d is what, as we have considered before, d is nothing but m 0 0 m inverse. So, we can directly write z k del k as m0 0 m inverse zk plus 1 del k plus 1. So, it is a set of the differential equations where zk del k combinedly will have the 2n vectors, n for z and n for del, m0 0 m inverse is 2n by 2n matrix, zk plus 1 del k plus 1 again a vector of 2n cross 1. So, this is my difference equations which can be solved utilizing the endpoint condition. So, if I will solve this, so my solution of the equation will be zk del k, which is m to the power kf minus k 0 0 m to the power minus kf minus k zkf del kf. So, this I am writing in terms of the zkf del kf simply by changing the matrix, system matrix, which is given here, and that we can see as we are saying zk m to the power kf minus k z kf, which we are getting by m to the power kf minus k zkf, and this term will be 0. So, zkf I am representing simply as m to the power minus kf minus k zk, while my second equation is in del k, which already is m to the power minus kf minus k del k. This we are getting from the second equation. This del k is 0 and m to the power minus kf minus k del k, and this now I am representing my system in terms of z of kf del of k. This will be nothing but my kf minus k 0 0 m to the power minus kf minus k, and this side parameter will be now zk and del k. So, this representation we can transform into zkf del k in terms of the zk del kf. Now, we see my endpoint transformation lambda of kf as f of x of kf. See, I am saying lambda of kf as f x of kf. Now, from equation 11, if k is taken as the kf, I can write x kf and lambda kf in terms of the w1, w12, w21, w22 and zkf del kf. So, first is my lambda of kf is w21 z of kf plus w22 del of kf. This is, and this equal to my f, what is x of kf, that I can see here w11 z of kf, w12 del of kf. W11 z of kf and W12 del of kf. So, I have to represent del of kf in terms of z of kf. As we are representing lambda kf in terms of the kf, we are trying to see can we have a relation between del of kf and z of kf. So, what we are writing W21 z of kf, W22 del of kf, f of W11 z of kf, W12 del of kf. So, we are arranging the elements of del of kf one side, z of kf on other side. So, this is W22 plus f W12, sorry, minus f W12 multiplied with del of kf, and this is equal to W12 minus f W11 z of kf with negative sign. So, we are writing W22 minus f W12 del of kf and W12 minus f W11 with z of kf with negative sign. So, del of kf we can simply write as W22 minus f W12 inverse with negative sign multiplied with W21 minus f W11 z of kf, and along with this negative sign, this whole we represent as T of kf. So, we are writing a transformation del kf as T kf z of kf. So, just by arranging these elements of z and del, we can write del of kf as T of kf z of kf, where T is nothing but minus W22 minus f W12 whole inverse multiplied with the W21 minus f W11. So, this give me the transformation of del of kf in terms of the z of kf. Now, we are utilizing a relation given by the equation 14 as z of kf equal to m to the power minus kf z of kf and del of k as m to the power minus k del of kf. From this we are using the relation del of k as m to the power minus k del of kf, and del of kf we just have shown that equal to T of kf z of kf. So, this is m to the power minus k T of kf z of kf, and z of kf we have taken from our equation 14 as m to the power minus k z of k. So, by this transformation what actually we are getting? We are getting a relation between del of k and z of k. So, this whole m to the power minus k T kf m to the power minus k, this whole we are using as T of k. So, by the first relation we say, by this we have shown that del of kf as T of kf z of kf, and by this new relation we are showing del of k as T of k z of k, where if we will see what is the T of kf, in this T of kf is given by a matrix relation given in f and w, and T is given in terms of m to the power kf minus k, T of kf m to the power minus kf minus k. So, with these two transformation, now we can write what is the transformation of lambda k equal to pk xk. So, now consider my transformation lambda k equal to pk x of k, and again lambda and x I will represent in terms of the W11, W12, W21, W22. As we have seen here, xk I can represent in W11, W12 form, and lambda k in W21, W22. So, lambda k is W21 zk and W22 del k. So, lambda k I am writing as W12 z of k plus W22 del of k, this is my pk and xk in terms of W11 and W12. This is W11 zk plus W12 del k. Sorry, this will be not W12, this is W21. Again we will arrange the elements of zk and del k. What we will? We use the transformation del k equal to tk zk. So, we write W21 zk plus W22 tk zk, and on this side also pk is W11 zk plus W12 tk zk. So, the whole equation I am representing in terms of the zk, which can be cancelled out. So, I have W21 plus W22 tk as pk W11 plus W12 T of k. So, I can write my Riccati coefficient as post multiplying the inverse of W11 plus W12 tk. We have to post multiply. So, my first term will be W21 plus W22 T of k, and then multiplied with the inverse of W11 plus W12 T of k inverse. So, with this I get my pk as W21 plus W22 tk multiplied with W11 plus W12 tk inverse, and tk is given as m to the power kf minus k, this whole multiplication which is representing nothing but my T of kf m to the power minus kf minus k. So, this is represented as my tk. So, for a time varying case, finite horizon problem, I can find my Riccati coefficient Pk in terms of the elements of my model matrix and Tk which will depend upon the solution of your which will depend upon the eigenvalues. So, this my eigenvalue and the eigenvector approach to find out the Riccati coefficient Pk, which is required to determine the controller gain. So, for time varying finite horizon problem, I find out Pk equal to this. As my Kf approaches to infinity, so I can see in my Tk, Kf is approaching to infinity. So, this term is going to be 1 upon m to the power infinity, giving you the infinity and making this term to 0. So, as Kf approaches to infinity, my Tk will approach to 0 value. If Tk will be 0, so Pk is simply represented as W21 and W11 inverse. As Kf approaching to infinity, so my this problem is infinite horizon So, for infinite horizon problem my Pk will be this, for finite horizon problem I can find out my Pk as given by second equation. So, by this approach analytically we can find out what is the solution of my matrix difference Riccati equation. So, I stop my discussion here. From the next class we will start our discussion on the dynamic programming. Up to this we have discussed how we can use the calculus of variation to solve a optimal control problem. Our approach is for the given system which is represented in the state space, we are trying to find out the optimal value of the u which is minimizing a given performance index. In finding the optimal u, we require the Riccati coefficient P to be determined, and P can be determined by the solution of my Riccati equation either in continuous time or in discrete time. And for both the cases we have seen that how we can find out the solution for the Riccati equation directly in terms of the differential or the difference equation solved by using the any numerical technique or solved by some analytical approach. From the next class we start our discussion on the dynamic programming. Thank you very much.